Hello, in this video we're going to take a look at a couple of examples of integration using substitution. So this is going to effectively be the inverse of the chain rule. So when we're going backwards, what we're really looking for, finding these antiderivatives, is the same type of thing we were looking for when knowing when to identify using the chain rule. Our first example here, we have the integral of 9 times the quantity 5x minus 17 to the 6th. Now that 5x minus 17, we could, if we wanted to, go ahead and multiply that out. Multiply 5x minus 17 by itself a total of 6 times, and then distribute the 9, and then we wouldn't have to use substitution. But multiplying that out would probably take about a page worth of work. And if we use substitution, we can do a little bit quicker. And so the same type of thing that we were looking for to use the chain rule for our inside function, we're going to let our substitution substitute in for. And so here this 5x minus 17 is raised to the 6th power, so we're going to let u be that quantity. Now we need to substitute in for every part of this integral, and the main thing we need to substitute in for is our dx, because we want to integrate this with respect to u instead of x. And so we're going to take the derivative of both sides. So the derivative of u is equal to derivative of 5x minus 17 is 5, and then technically we've got du over dx. Well, what we're going to do is we're going to think of that dx as multiplying by both sides, and we get du equals 5 dx. Now, we want to substitute just in for dx, not 5 dx, so let's divide both sides by 5 here, and we'll get 1/5 du equals dx. Now this part, you can probably skip some of those steps once you get used to it. Alright, so if we plug back in, we didn't do anything with our 9 out front. Inside the parentheses is what we called our u raised to the 6th power, and our dx we said is equal to 1/5 du. Now we have our variable and our differential are in the same variable. If this is not all in terms of whatever the variable is that we're dealing with here, if we still have x's left here, then we're either not done with our substitution or it cannot be done using this integration method. Alright, so if we clean this up just a little bit, we can multiply our 9 and our 1/5, and we get 9/5 times u to the 6th. Now we are ready to go ahead and integrate this. The integral of 9/5 there is just a coefficient, and the integral of u to the 6th du is going to use that power rule. We'll get u to the 7th over 7 plus our constant of integration c, and we can multiply that, kind of combine those constants. So 9/5 times 1 over 7 is going to be 9 over 35. We do need to go back in terms of our x value, so we're going to go back to our substitution. Our u was equal to 5x minus 17, so this is going to be 5x minus 17 to the 7th plus c, and then just like we've seen in other integration methods, we can take the derivative of this and we should get back where we started. Alright, let's do another example. Here we have the integral of 2x plus 7 over the quantity 3x squared plus 21x to the 5th. And so if we were doing a derivative on this, our inside function would be what's inside the parentheses there on the bottom. That is what we are going to let our u substitute for. So u is going to be equal to 3x squared plus 21x. And when we take that derivative, du is equal to the derivative of 3x squared is 6x, the derivative of 21x is 21, and then I'm going to multiply both sides by that dx. We need to get that dx by itself so that we can substitute in for it. So we're going to get 1 over 6x plus 21 du is equal to dx. right? When we plug back in, we haven't done anything with that 2x plus 7 just yet, so we'll leave that in the numerator. In the denominator, that's what we called our u raised to the 5th power. And then dx is 1 over 6x plus 21. Now, we cannot integrate this until everything is in terms of, oh, sorry, that should be a du right there. We cannot integrate this until everything is in terms of whatever the variable is in our differential. Our differential here is a du, so we need to get rid of all of our x's. Now, we can't just make them disappear unless we can use algebra to simplify this. And I'm seeing a little bit of a pattern here. 2x plus 7 and 6x plus 21 do have some common factors there. If I factor out that GCF in the denominator, we get 1 over 3 times 2x plus 7. And now everything's multiplied, everything is factored. We can divide out that common factor of 2x plus 7. And that's going to leave us with 1 over u to the 5th times 1 over 3. I'm going to go ahead and go back up here. And so in order to use the power rule, we like to have that u in the numerator. So I'm going to write this as 1/3 times u to the negative 5th du. Just bringing that u to the 5th from the bottom up to the top and making the exponent negative. We still have the 1 over 3 as far as our coefficient. And when we integrate that, we get 1/3 times u to the negative 5th plus 1. Negative 5 plus 1 is negative 4. Divide by our new exponent. Don't forget your constant of integration. And so this is going to end up being a negative 1 over 12. And then u to the negative 4th is the same thing as putting that u to the 4th, and our u is 3x squared plus 21 raised to the 4th on the bottom. Put that 1 in the middle. And then we still have our plus c on the end. Again, you can always check your work by taking the derivative, using the chain rule most likely, and getting back what you started with. All right, let's do one more example. Here we have the integral of x times the square root of 7x minus 5 dx. So again, if we were taking a derivative of this, we would be using the chain rule because that's 7x squared minus 5 underneath the square root. And so that's what we're going to let our u substitute for. And so our du, derivative of 7x squared minus 5, is 14x dx. Now we've got that x there, so I'm actually going to do a little bit, I'm going to put these two pieces together. They're all multiplied, and we're multiplying with real numbers. We can switch the order. So I'm actually going to keep that x and that dx together and only move the 14. What that's going to do is save us that step of simplifying once we get it all plugged in. So I'm going to replace my x dx with 1 over 14 du, and then our u is going to substitute in for that 7x squared minus 5, but that is underneath the square root. So if we get this ready to integrate, I'm going to go ahead and pull that 1/14 out front. The square root of u is the same thing as u to the positive 1/2. So when we integrate that, we're going to get 1/14 times u to the 1/2. If we add 1 to that, we are going to get 3/2 divided by our new exponent plus c. And then dividing by 3/2 is the same thing as multiplying by 2/3. And when we simplify that, 1/14 times 2/3, we've got a common factor of 2. So we get 1 over 7 times 3, or 1 over 21, times our u was 7x squared minus 5 raised to the 3/2. And then don't forget your plus C on the end. All right, I'll see you guys next time.